All right, welcome to Chapter 5, which is more or less an extension of Chapter 4. There is a small change that we are going to make to the type of example that we are going to use, but it's just a small change, so let's not get too bugged about it. In Chapter 4, we wanted to know if there was a significant difference between a single score and a group of other scores. We talked about a sample of one individual, compared to a distribution of many scores. We wanted to know if that score is significantly different. Well, the change that we are going to make in this chapter is that we are going to not compare a single score to a population, but we are going to compare a small sample of people, so the mean of a group, to a population of scores. So there is a small difference there, but it is very meaningful, and we're going to talk a little about the logic and what the changes are. So just to give you a brief synopsis of what we're talking about, a single sentence thumbnail sketch, we are comparing the mean of a group to a population of individual scores. If we use the example from last chapter with the vitamin and the baby walking age, then if I were to morph it into what we're going to be talking about in this chapter, instead of saying, does a single baby's walking age significantly change with the pill compared to individual population of babies, I would say, is there a significant difference in the mean of a group of babies that took the pill compared to a population of individual scores? The difference is that we're comparing the mean of some scores as opposed to an individual score. So let's go ahead and jump into the example for this chapter so that we can kind of put some kind of theory to it. Social psychologists, so obviously this comes out of social psychology as a theory, have wondered if known positive traits of a person, which we kind of call character, so if somebody is nice and warm and compassionate, if knowing the positive traits of a person would increase the perception of attractiveness of those individuals. So if you look at a picture of somebody and you are told things like, well, that person's a humanitarian, they give money to the Cancer Society, and they like to help old ladies across the street, would that increase your perception of how attractive that person is? So in this example, we had 64 people that were told that the individuals in a series of photographs have positive traits, that they're kind, warm, intelligent, etc. These 64 people rated the pictures on a scale of 0 to 400. Don't ask me where they got their scale from. I didn't design it. And a mean rating is produced. So in this example, we have 64 people that rate people based on their attractiveness, knowing that they have positive traits. And the average rating for those 64 people is produced. The results are to come. We're going to walk through a couple other aspects of this example first. In this example, we have a large group of people who also rated the pictures. So when we talk about a large group of people, we're talking about the population that we are comparing our sample to. However, the group that we're comparing our sample to knows nothing about the pictures. They just see people and they're going to rate them. So they aren't influenced by the character of the individuals. A big hint here is that this is our comparison distribution. This is the group that we are going to compare our sample to. With the group that knew nothing about the pictures, so our population, on average, they rated the pictures as a 200 on a 0 to 400 scale, and the standard deviation was 48 points, whatever those attractiveness rating points are. So if we were to develop a curve of our comparison distribution, it would look like this. We have a population that we are using to compare our sample to. The rating, or the raw scores for the population, has a mean of 200 and a standard deviation of 48. So 200 is the mean. Standard deviation of 48 means that 248 and 296 are two standard deviations above the mean. And then 152 and 104 are two standard deviations below the mean. And those are the same z-scores that we've been talking about. Also, these are the number of standard deviations. So it's either z or standard deviations. And we have a standard deviation of 1 and 2, and of -1 and -2, and a mean of 0. So nothing new here. Okay? Our sample distribution is going to be a distribution of scores based on the attractiveness ratings that 64 people have for the images. So our sample n, so the number in our sample, is equal to 64. And those 64 scores are going to represent some kind of normal curve, and that sample of 64 people will have a mean of something and a standard deviation of something. We don't know those numbers yet. We haven't gotten that far in the example. But we do know that we are going to be comparing the mean of a distribution of 64 people that we're told that the images have positive characteristics, and we're going to compare that sample to our population. Now, here's where the trick happens. Last chapter, we compared an individual score with a distribution of individual scores. Okay, you got to listen to that language very carefully. We compared an individual score, so for example, an individual baby's walking age, to a distribution of individual scores of the rest of the babies. So it looked like this. We looked at the single score to find out where it fell on our comparison distribution. Here's the thing about this chapter. Now we are comparing the mean of one group to a distribution of individual scores. So here's what we're doing. We are taking the mean of a sample of 64 people, and by the way, this distribution is just arbitrarily placed on our comparison distribution. There is nothing to be said for why I chose to put it 2 standard deviations above the mean. It's just a demonstration. Okay, so our population is, in this case, is the distribution of individuals who were told nothing about the pictures. That's the larger curve. And that has theoretically infinite amount of people in it. It doesn't matter how many people are in that distribution. There's just a lot of other scores. The sample is a smaller distribution of 64 individuals, and we are trying to determine if that distribution is significantly different than what the comparison distribution is. Now, you might already be thinking to yourself, well, wait a second. We're comparing the mean of 64 scores to all these individual scores. And if you remember correctly, there is a problem there. And the problem comes in with the central limit theorem. So we can't compare the mean of a group, so the mean of 64 scores, to a distribution of individual scores. And it's because of the central limit theorem. And if this doesn't click right now, I think it'll become a lot more sensical to you once we get to the example. The central limit theorem states that the larger the group is, the less spread out the group is. That means that as you get more scores, the average tends to be more representative of the central limit theorem states that the larger the group is, the less spread out the group is, meaning that the more people that are in the group, the less likely the scores are to vary from the mean. That is, the mean will be very representative of the central tendency, and that the standard deviation will become smaller because as you get more scores, they tend to cancel each other out because you will have as many scores above and below the mean. So in an individual group of scores, or a group of individual scores, the cutoff score would be much too extreme for the mean of a group of scores to be ever significant. Okay, I'll say that again, maybe in a different way. If we used a cutoff score on a distribution of individual scores, that cutoff score would be far too extreme for the mean of a group of scores to be far enough away from the mean of the individual scores to be significant. Okay. Here's the good news. The good news is that with little effort and only a change to step 2, which is where we describe the characteristics of the comparison distribution, we will convert the comparison distribution of individual scores to a distribution that looks more like the sample. Really what we're going to do is we're going to take our comparison distribution, which is of a bunch of individuals, take the mean of that group many, many times, and create a new distribution. Here's what it looks like more or less graphically. So if this doesn't make sense to you, again, we're going to go through an example that I think will clarify things. So here is the basic idea behind the distribution of means. If we were to randomly select the mean of n scores, so the mean of some number of scores from a distribution of scores to create a new distribution, we would have created a distribution of means. Another way of saying it is that we are going to create a distribution of the means of scores from the individual distribution, from the comparison distribution. So, for example, let's say that I had a sample of 5 individuals and I asked them the attractiveness rating of the individuals knowing the positive characteristics. Let's say it's only 5 in this case. I could take that mean and that would be the mean of my group. Now, with the distribution of means, we are using the comparison distribution, not the group that we're sampling to find out if there is an effect, but the group that we are comparing it to. So I would go back to the comparison distribution of these individuals that I've taken the attractiveness ratings on for the people who don't know anything about the pictures. I would take 5 of those scores randomly. I would take the average of those scores. So I would take the average of the scores, which is sum of the scores divided by n. So I would take 5 scores, add them together, divided by the number, and I would create a new histogram. I would do this process where I take the average of 5 scores many, many times. It doesn't matter how many, it's theoretically infinite. But if I did it 1,000 times, I would have 1,000 new scores that are the average of 5 scores. What I would come up with is a distribution of the means of scores that has the same mean. So mathematically, the mean stays the same. So if I take the average of all these 5 scores many times, the average of the individual distribution will be the same as the distribution of means. But the spread of the scores will be much narrower because I will take these 5 scores and the average of these 5 scores, for example, might be somewhere in here. And if I did that again randomly, I take 5 scores, the average of those scores is again going to be somewhere in the middle of all these individual points. So that means that when I plot these individual means onto a new distribution, the scores won't be very spread out. They're going to be a lot more narrow. And that is what we use to compare the mean of our sample to a distribution that is much more narrow that fits the same narrow characteristic of our sample. So, the shape of the distribution of means changes depending on how many scores you have in the distribution of means. If I have a sample of n equals 1, so that means if my distribution of means is the same as my distribution of individual scores, it will have this kind of wider normal curve shape to it. If my distribution of means is the means of 10 scores, then that distribution becomes a little bit narrower. It's not as wide. And then if I have 100 people in my sampling distribution, it's going to be even narrower yet. So the more scores we average together, the narrower the curve becomes. This is just a demonstration of what the curve looks like. We tend to not change the distribution shape for every example. What we normally do is just use some curve that is narrow altogether, and that just becomes demonstrative of the narrowness of the distribution of means. So don't get too bent out of shape of whether or not your curve is narrow enough. Really all we need to do is show that it's narrower than the normal curve. The good news is that only step 2 is affected. So what we do to create a distribution of means is we take a sample of the number of people in our actual sample. So we sample 64 scores in this case from our comparison distribution. So we take the mean of 64 scores, because that's the number of scores in our example that we're working with. We take the average of 64 random scores from the comparison distribution. We plot them on a new distribution and we get a distribution of means. We do this many, many times, and this is actually a histogram that is of the means of 64 scores taken multiple times. This is what we will use for our new comparison distribution. Now, you might be thinking to yourself, how do we actually do that, considering we have to take 64 random scores, average them, and plot them on a new distribution? Well, the good news is that we get to use a few rules in order to do that. We use these rules, which are in the green box, to create our distribution of means that has a similar mean but a narrower spread. So in our example that we are working with, the mean score for our population, so remember we're using this population symbol. This means that we are using population mean of 200. We discovered that based on the example above. You can go back to that slide and take a look at it. But the mean of the population is equal to 200. That means that the average rating for the people that were told nothing about the character of the people in the pictures rated the individuals at a 200 on average. The standard deviation was 48. That was given to us in the example. Now, you might be thinking, wait a second, this is variance. This is our population variance, and it's 2,304. That wasn't given to us. You're right, it wasn't given to us. But we know that when we calculate standard deviation, we actually take the square root of the variance. So that means if we're given the standard deviation, we can square it, and that gives us our variance. So the variance of the distribution of individual scores is 2,304. That becomes helpful to us in the next set of steps. So we have kind of the characteristics of the comparison distribution here. We need to convert our distribution of individual scores to a distribution of means. And here's how we do that. The mean of the distribution of means, that little m there stands for the distribution of means. So if you see a little m there, it means that we're talking about the distribution of means and not just the mean of the comparison distribution itself. The mean of the distribution of means is equal to the mean of the population. Well, that's handy, because that means all we have to do is look at the mean of the population, which is 200, and that is the same as our mean of the distribution of means. Great. We don't have to do any real work there. The next step, the variance of the distribution of means is equal to the variance of the population divided by the number in the sample. Remember, n is equal to the number. So I can take the variance of the population, which is 2,304. I can divide it by the number in the sample, which is 64, and that gives me 36. 2,304 divided by 64 is equal to 36. The next step is to calculate the standard deviation of the distribution of means. And if you remember from calculating standard deviation, in order to get standard deviation of the variance, we take the square root. So the square root of what we found for the variance of the distribution of means, which is what we found in the last step, 36. Another way of doing this is to take the square root of the variance of the population divided by n. These two are similar, because we know that the square root of the variance of the distribution of means is equal to the square root of the variance of the population divided by n. Those are the same things. We just found that in step 2. So we can use either one of these steps, but it's usually easier just to take the square root of what we found in step 2. The square root of 36 is equal to 6. So what we have found is our comparison distribution, which is now a distribution of means. In step 2, we converted the distribution of individual scores to a distribution of means. The distribution of individual scores had a mean of 200 and a standard deviation of 48, which looked like this. In the last slide, we used our rules to create a distribution of means, which means that we now have a mean of 200, a standard deviation of 6. This distribution is our new comparison distribution. The mean of 200 plus the standard deviation of 6. So that means 206 is the first standard deviation, the second standard deviation is 212, and the first standard deviation below the mean is 194. The second standard deviation below the mean is 188. So our new comparison distribution has a mean of 200, standard deviation of 6. That is what happens in step 2. We're now going to step through the 5 steps of hypothesis testing using our example. We are going to find out if there is a significant difference between a group of individuals, 64 of them, that rated photographs that they had known positive traits compared to a bunch of individuals that rated the same pictures but knew nothing about the character of the individuals. So let's go ahead and work through that. From the top, Social psychologists have wondered if the known positive traits of a person, also known as their character, would increase the perception of attractiveness of those individuals. 64 people were told in a series of photographs that they have positive traits, that they're kind, warm, intelligent, and so on. You know, things like me. 64 people rate these pictures on average as 220. So our sample's mean is 220. Already we know that that sample mean is 20 points above the population, but we want to know if that's significant or not. In this example, a very large group of people also rated the pictures. However, the group was told nothing about the characteristics of the people in the pictures. Again, this is our comparison distribution. These are the individuals that were told nothing and rated the pictures with no other information. On average, the group that rated the pictures, not knowing the positive characteristics, rated them as a 200 on a 0 to 400 scale. The standard deviation of that group was 48. We kind of already know that because we walked through a couple of the earlier steps, but we're just reiterating it for now. Step 1. We need to restate the research question as a research hypothesis and null hypothesis, and also identify the populations. So the research question comes from the actual example. The research question is this: is there a significant positive difference between the group that rated the individuals knowing positive characteristics and those that rated the individuals without knowing any positive characteristics? Our research hypothesis is that our sample mean, which is of the 64 people who knew the positive characteristics, would have greater ratings. That means that they would find them more attractive than the population mean, which is the individuals who rated the pictures with no other known characteristics. Another way of saying this is that the sample mean, capital M, will be greater than the population mean, mu. The null hypothesis is a statement that there won't be a significant difference. In other words, the sample mean of individuals that knew the positive characteristics of the individuals in the pictures would have lower or equal ratings as the population that knew nothing about the pictures. So in this case, there is no effect. Another way of saying it is that if the null hypothesis is true, it means that knowing positive characteristics about the individuals would not increase the ratings. Another way of saying that is that the sample mean is less than or equal to the population mean. Remember, we use this mathematical representation in order to make our conclusion in step 5, so we do want to know that. Now, the reason why we use these symbols, greater than and less than or equal to, is because of the number of tails. This is a one-tailed test, remember, because we are trying to determine if there is a positive increase. We're not saying that we don't know what the increase or decrease might be, so we're going to go with non-directional or two-tailed. We actually are hypothesizing that there will be an increase. So that's a directional test. Population 1 in this case is the individuals who know the positive traits, and population 2 are the individuals who know nothing about the people in the pictures. Again, one of the drawbacks of the way that this text uses population is that they are using population as kind of a name for group. So really we can say group 1 and then group 2, or we can say the sample and the true population. I think that by now we kind of understand that and we can work with it. Step 2. We need to identify the characteristics of the comparison distribution, which in this case is the distribution of means. So here are the characteristics of the population and the sample. I always like to talk about the sample characteristics at the same time because I think that we're smart enough to keep them separate, but also any information is good information to have. So in this case, we know that the population mean is 200. That's the population of people that don't know anything about the people in the pictures. The standard deviation of the population is 48. The mean of the sample of individuals that rated the pictures knowing positive characteristics is 220. And the number in the sample is 64. We've already worked through this, but I'm just reiterating it for due diligence. We went from a distribution of means. Let me label that. We went from a distribution of, individual scores. So this is a distribution of individual scores to a distribution of means. So this is a distribution of means of scores. In this case, Pardon me. In this case, we went from a distribution of individual scores that had a mean of 200, standard deviation of 48. We used our rules to create a distribution of means that has a mean of 200 and a standard deviation of 6. We did this earlier in the lecture, and this is a reiteration of that. So our new distribution is a distribution of means that has a mean of 200, standard deviation of 6. And maybe I'll make that notation here as well. Right. So the mean of the distribution of means is equal to 200, and the standard deviation of the distribution of means is equal to 6. So that's all the information we know about our new comparison distribution. That means we get to move on to step 3, and we have to find out the cutoff score, the score at which we will reject or fail to reject the null hypothesis. We're going to use an alpha level of less than 0.05. Another way of stating the alpha level is to use the alpha symbol equals 0.05. Alpha is just another way of saying what is the point at which we will reject or fail to reject the null hypothesis. We also call this the cutoff score. So our cutoff probability or our alpha level is 0.05. The direction in this case, which we established in our hypothesis set up in step 1, is a one-tailed test because we are trying to determine if there is a significant positive change. I'm going to erase that. Boop. So we can consult our z-table to find out what the appropriate one-tailed cutoff score is, or you can use the cheat sheet that we looked at in a prior chapter. The cutoff z-score, or the alpha level, is positive 1.64. What that means is that if our score is less than 1.64, then if it is greater than 1.64, then we will reject the null hypothesis. Because remember, z-scores are expressed like this. So if our sample's z-score, if the mean z-score for our sample is greater than 1.64, we will reject the null hypothesis. In other words, we will reject the idea that knowing positive characteristics has the same or less or lower scores than those who know positive characteristics. We can move on to step 3, and we can calculate our sample's z-score. Now, we need to determine the sample score on the comparison distribution. We need to find out where our sample's z-score is on the comparison distribution. We're going to use a formula that looks very similar to the z formula from chapter 4. In chapter 4, the z formula was z-score is equal to the score that we are using. In that case, it was the baby walking age, minus the mean of our comparison distribution divided by the standard deviation. Now, in this case, we are using a similarly structured formula. The mean of the sample, which is the mean of those 64 scores, minus the mean of the comparison distribution, which we found in step number 2, divided by the standard deviation of the comparison distribution. Of the distribution of means. It is a comparison distribution, but it's a distribution of means. We plug in our numbers that we discovered in step 2 and 3. 2 and 3. Z-score is equal to the mean of the sample. In that case, it was 220, minus the mean of the comparison distribution, which is the distribution of means, which is 200, divided by the standard deviation of the distribution of means, which we found to be 6. 220 minus 200 is 20, divided by 6 is equal to 3.33. Our sample's z-score is 3.33. So the mean of the group of 64 had an average rating of 220. That z-score is 3.33, meaning that having a sample mean of 220 equals a z-score of 3.33. On our comparison distribution, a z-score of 3.33 is well above our cutoff, but we need to rely on actually going through the process to do that. Just for clarity, by the way, I will quick plug in the sample's raw score, the comparison distribution's raw scores. We had a mean of 200 and a standard deviation of 6. So that means one standard deviation above the mean was 206, 2 was 212, 3 was 218. If I were to go up another standard deviation, it would be 224. And that helps us to understand how excuse me, our sample's mean of 220 fits at approximately 3.33 standard deviations above the mean. Okay. So let's go on to step number 5, to determine what the results of our hypothesis testing are. Remember, we bring forward the null hypothesis from step number 1. And in this case, it was the sample mean is less than or equal to the population mean. And we know that population 1 was our sample and population 2 was our actual true comparison distribution population. So population 1, our sample, is less than or equal to population 2. We bring forward our population 1 z-score, which was our sample z-score of 3.33. We bring forward our comparison distribution z-score, which is our cutoff z-score of 1.64. And we have to make a logical conclusion about this mathematical statement. So we just ask a simple question. Is 3.33 less than or equal to 1.64? That is false. So that means that we reject this statement. We reject the idea that population 1 has a lower or equal to score as the population 2, which is our comparison distribution. Here's what we have to say about the results of our study. We reject the idea that the individuals who rated the pictures, knowing that they had positive qualities, would rate them at the same or lower than the individuals who rated the pictures with no other known information. There was a significant positive difference between the two groups. That last statement, there is a significant positive difference between the two groups, is kind of what we found here. There is a significant positive difference in the z-score for our sample compared to our cutoff z-score. Overall, we found that there is a significant positive increase when somebody knows that the people in the pictures have positive characteristics compared to those who know nothing. So what we've done here is we've stepped through a hypothesis testing procedure that allows us to test the difference between groups when there is a mean of a group compared to the individuals in a comparison distribution. I encourage you to take a look at any additional resources that are available. If you want to take a look at external resources that I didn't provide to you, please do. There are lots of resources available, and I don't proclaim that everything that I give to you is the end-all be-all. So please use whatever learning tactics you are familiar with, and if you have questions, you can ask me. You can ask me personally, or you can ask me through the course room. Through Blackboard's discussion board for Ask Your Instructor. You can also ask questions of your classmates, and you can use the discussion boards as a way to elaborate on some of the ideas given what you've learned in lecture. A lot of times it helps reinforce learning too. Other than that, I look forward to seeing your work, and we'll catch you next time.